So we are here, we're going to be talking about liquid nitrogen primarily today. We do nuclear fusion research for the Department of Energy, and in that research we have a lot of interesting science, technology, engineering things that we do. But one of the most important fundamental things is learning about states of matter, solids, liquids, gases, and plasmas. So we've discussed plasma earlier today, and now we'd like to talk about gases and liquids. And we'll use the old standby liquid nitrogen. Now, nitrogen is found in the air as a gas, and if one cools it down enough, it can be liquefied. Dr. Boom and I will talk about how we can use it in today's research environment. But right now, let me just pour a little bit of very cold liquid into some relatively warm, simple water and see what happens. So I do have some safety glasses on.
So we're going to see if we can make Rick disappear.
You're going to make me disappear?
Make you disappear.
There we go. Okay, Dr. Boom. Now, Dr. Boom, you know what the interesting thing is?
What?
We had water down here, of course, right?
Yeah.
We had water, and then we poured in a few liters of liquid nitrogen. And what we see here is actually water vapor. We don't see the liquid nitrogen. The liquid nitrogen, or gaseous nitrogen, is clear and colorless. What we do see here, though, is water vapor, just like a cloud. So that water vapor here has cooled down enough so that we can see it. And because it's cold, it's more dense than the air around here.
Because it's colder than the air around here.
Right, so it's more dense.
It's more dense, and that's why it goes down instead of up.
Yes, so this is not steam in the sense that we think of steam from a boiling water, a kettle of boiling water on the stove.
But you can get water vapor from a boiling water in the stove.
That's right. You do get water vapor from boiling water on a stove.
Right.
And that water vapor is less dense than the surrounding air, so it tends to float.
And
this is more dense.
Oh.
So you can see how it falls over the edge.
I can feel how cold it is.
I mean, we could even pour this out.
Oh, look at that.
Just the vapor part.
It's like the fog.
Just the vapor part. And you'll actually notice in the mountains sometimes where there's cold fog, you'll actually see it pouring over the mountains. So this phenomenon is not just for liquid nitrogen and water. We see things like this in our natural habitat.
I see the marine layer coming in every night, well, some nights, and it stays down just like this because it's cold.
It's because it's more dense.
More dense.
Let's use the word more dense.
Yes,
it
good
may
idea.
It may be colder, but the idea is it's more dense.
It's more colder than the air around it. Okay. So what else are we going to do for these guys?
Okay, so we have a lot of, I think, some interesting concepts here. We want to show them things about, like just what we talked about, expansion, contraction, more dense, less dense, energy when we cool things down, and water vapor from the air here will actually condense onto a surface. So we actually have cryogenic pumps. And we'll show you an example of a cryogenic pump here.
But first, I'd like to pour it on this table saw because...
Oh, no, not again, Dr. Boom.
Yes, again, because this table saw is relatively warm compared to this liquid nitrogen.
What is the temperature of that liquid nitrogen?
I don't know, I thought it was around here somewhere.
Oh, it says minus 196 degrees C.
Whoa.
And that table saw is about, 20 degrees C on the positive side.
Yeah, it's not that
So
cold.
we have about over 200 degree difference here.
Wow, so this would be like boiling.
Oh, yeah, similar.
Let's see.
Way over that.
You gotta be careful so it just comes out a little bit.
Oh, I see the fog. That's kind of...
Yeah.
Any liquid coming out?
The liquid's coming, but it's not here yet. There it is.
Oh, it's running off.
Yes, there it is. It's running off. So
There's some on this side. I can see it.
Yeah, you see that? It like skitters across on its own gaseous underside. And so that's called the Leidenfrost effect.
The Leidenfrost effect.
Yeah, look at it. Just skittering across and boils off.
That is awesome. So it has, I can kind of see it. It has a little cushion. The blob goes down, and then as it warms up at the base, there's a little cushion of that vapor.
Watch your feet. Here
And
comes
so
more.
the blob just goes right on across, moves around, friction-free. Now,
There it goes.
your grandparents may have done this as well when they're cooking in cast iron skillets,
So you
or
can
your parents.
do that with water.
Yes, you can do it with water on a hot skillet. Now, it's a little hard to see, and I'm not sure if the camera is picking it up. But
Well, I can send some more.
send some more. Okay, the Leidenfrost effect, and I think
it.
that came about from a couple hundred years ago. Very interesting, very interesting. Okay, so one thing about molecules of gas, as they move around, they have energy because they're moving, so they have kinetic energy. And when you blow air into a balloon, for example, that balloon is, we call it, inflated. And that's because the molecules inside have adequate energy to overcome the elastic stretch of the balloon and actually expand it. Now, if we could somehow cool those particles down inside, then we could actually slow them down and have less pressure, less force, and we could allow that balloon to kind of collapse. So there's some interesting things that we're going to show here. Another thing we can show, here we have a simple, very simple empty, we would say it's empty. It is empty of water, a plastic bottle. And it's a relatively thick one, and not super thick, but it's not real thin. And it just has air in it at atmospheric pressure. What we'd like to try is see if we can cool this air down like we will with the balloon. So these will be two examples of the same thing if you can try that.
Well, let's see the balloon here. Now, what do we think is going to happen? Is this balloon going to explode like balloons usually do when you go boom?
Well,
or is this balloon going to, what?
I don't
What's it
think
gonna
it'll do anything.
You don't think it'll do anything?
I think there's probably three
Yeah.
or four things it could do.
Could float.
It could float, it could sink, it could explode, it could shrink, it could just simply
there it
break.
is. It's shrinking. So why is it shrinking?
Oh, this is what I was talking about. I haven't
It's
actually
shrinking.
seen that though. So we've removed kinetic energy from those molecules inside of there.
Wow.
And now they don't hit the sides of the balloon so quickly, and now they don't put the force and therefore the pressure on the sides of the balloon.
And we do have liquid inside the balloon. I can hardly see it. Let me try this again with a clearer balloon.
I see that it's expanding back though.
It is. It's coming back. Holy smokes. We didn't put any gas in or take out.
No,
That's amazing.
and no molecules were harmed in the making
Molecules.
demonstration.
And here we go again, and we can see the liquid.
Oh, yeah.
Liquid oxygen and liquid nitrogen.
Yep.
Because what's in my lungs when it comes out? Carbon dioxide, but very small amounts. And then there's oxygen and nitrogen. Wow. I hope you guys can see that. It's pretty cool. It's so cool. Okay, so let's try something else.
Now,
Here-
let's before we do that one though, before we do that,
Yeah.
this one has kind of semi-rigid walls.
Yeah.
And we'll see how well that works.
I can't pressure.
No, these were elastic.
Yeah.
And so those were kind of moved down. Now, the reason they actually closed were twofold. One is, yes, we're reducing the energy of the molecules inside of here.
Right.
But look, we have a whole room, a whole planet full of atmosphere that's just wanting kind of to push this in. So when we lose the energy in here and reduce the pressure inside, all of this other atmosphere is pushing on here. And so it makes it shrink. So it's kind of a twofold thing. If you were to do this up on the moon, nothing may happen. I don't know. We'd have to try that.
Oh, what? Yeah, what? I have the answer. The answer is this. It does not matter what the pressure is on the outside. What matters is the change of state of matter, because it changes from a gas to a liquid, and a liquid contains a whole lot less volume than a gas. Problem
Oh,
solved.
it
Look at
does.
that.
It does.
It does
huh?
not matter what the pressure is on the outside. Oh.
Maybe. Let's see. Here, take
All right.
off that thing.
Oh.
And let's see if we can make this this bottle shrink.
Now, this is an example. Watch. Yeah? Nothing happened. But if you put this on and you capture the gas in there, so no molecules can come out or go in,
May need some more. That's a kind of a stiff. Oh, no, there it goes. There it goes. All right, that's good. So even with that semi-rigid wall, if you reduce the pressure inside of there, it tends to collapse.
that's right. And the pressure on the outside does help it collapse.
Yeah. Wow, look at that. That is cool. Is that a crack in there now?
No, I don't think it is.
Okay. Well, so the idea here, when you're engineering things, you have to be able to engineer them properly. And you have to know these fundamental ideas. The vacuum chamber, did you know the vacuum chamber on our fusion device has some of its walls are 1 inch thick of stainless, of a type of steel.
Steel.
So it's very, very thick. Keep it from doing that. Very awesome.
All right.
Okay.
So we still
All
got
right.
time?
Oh yeah, yeah, we
Okay.
got plenty. Now that was kind of a shrinking balloon.
Yep.
Okay. Let's see what this actually looks like. Can you hold this up to the camera? Let me see
you
if I
can't.
have a.
You can look down inside of it. You get a shot of that?
So it looks to me like boiling water.
It does. And it is boiling, but it's boiling at minus 195 degrees C.
Way down there, huh?
Yep, way down there, because it liquefies at minus 196 degrees C.
Oh, I see.
So, but it's boiling, and so what happens when things boil? They go from liquid to gas.
Yes, they gain energy from the environment. They go from liquid to gas. That's what happens when
Yeah.
things boil. The vapor pressure of the surface of that of the environment right above here is the same as what's on that surface there. So that's boiling.
Okay.
All has to do with vapor pressure.
So, what should we do? Should I drink some?
No, don't drink any. But
Okay.
just in the time that you've had it here, just in that time, I've seen the volume here. The volume of the liquid has gone down.
It has.
So that must mean that it has evaporated. Some of it's evaporated away. But I couldn't tell how quickly it evaporated away.
Well, from my studies, liquid nitrogen at 1 liter would become 600 liters of gaseous nitrogen.
Okay,
Actually,
that's
a little bit more.
That's all fine and dandy.
So,
But how quickly does it do that? Does it do? I know that when I know when you have dropped an ice cube on the floor by the refrigerator, and you let it melt,
yeah,
and then that melt stays there for about a day or a few hours.
Yeah.
It takes a while for water to evaporate.
well, it depends on the heat transfer.
So I want to see how quickly this does in this environment here. So do you have a demo that can show us how quickly this happens?
Yes, it's called Oscar. We bring Oscar wherever we go to demo, and this here is Oscar. He's waiting to come out.
Oscar.
And you'll see Oscar all in his glory as soon as I can fill him up. No, I'm not filling up with liquid. I'm filling him up with gaseous nitrogen. So now we're going to make him come to life. And so let me get out of there, put some,
Oh, we can
Nice.
say hello,
hello,
or
Oscar.
we can say goodbye to Oscar.
He's only around for a short time.
So you put the liquid in the volume.
Oh.
Oh, bye, Oscar.
That was the end of Oscar.
You put the liquid in the volume, it turned into a gas, it expanded, and that expanded pretty quickly.
It did.
Much more quickly than my ice cube full of water spot on the
That's
floor.
true.
Okay. Cool.
And so you can see here on the outside, we have some condensation building up here.
Well, it's similar to the outside of this cup.
That's
and,
right.
And this will become more condensation. How could you use that for anything?
Well, it turns out we do use this, and we use liquid nitrogen and liquid helium inside in tubes in our vacuum vessel, and it condenses the gases that are inside of our vacuum vessel, and we call it pumping them. But it really, it takes them out of the volume of the vessel, and it condenses them on the cryo panel. We call it a cryo panel. So then after we're done running for the day, what we do is we warm these up and pump all the gases off, and then we're ready to go again.
Well, I don't understand it. If it's a vacuum chamber, why do you still have gases in there?
Because we put gases in at very low pressures, at 10 to the minus 4 torr, to produce a plasma. And our benefit for having these cryo pumps in there is that we can reduce the density of the plasma with the cryo panels during a shot. And so a shot is when we make a plasma to 150 million degrees centigrade, and we do gas it, and we do change its density. It's this guy right here.
This guy right here?
Yeah, this is the plasma right here, and then the cryo panels are down here. There's one shown right here, and there's one here and one here.
Oh, these little things, yeah.
Yeah, and so they are very instrumental in controlling the density in the plasma.
Oh, that's very good, Dr. Boom. I like that.
Yeah.
So this is a little picture, cartoon of the tokamak. It's got a vacuum chamber, some magnets, and more magnets. It's got those little cryo pumps. Awesome. And we're talking about liquid nitrogen, which is used in the cryo pumps, and in general, talking about states of matter,
Right.
Gases, liquids, solids, and plasmas. Very cool. Very cool. All
Now,
right.
I have one for you.
Uh-oh.
We're going to do an experiment. And so we know about the experimental method, right?
Yes.
And so the experimental method starts with what?
A question.
A question.
Sometimes. A question? How about that? Does it
No,
start with a question?
No, it doesn't start with a question.
observation.
What's anybody out there in TV land?
How about an
An
observation?
hypothesis.
How about an observation?
Observation. You win the prize. Okay. So we make an observation, and what's the observation? Well, the observation is we know water at room temperature has a certain density, right? And we know liquid nitrogen at minus 196 degrees is liquid. These are two liquids, and if we pour one into the other, which one's going to float?
Oh, you want to compare the density between liquid nitrogen and something we're familiar with, which is water.
Yes, liquid nitrogen at minus 196
How do we
degrees
tell
centigrade.
them? How do we tell the difference, though?
And
They
water.
both look alike.
Well, I have some water here, and it's in a cup, and it's green.
Green water.
Green water, and I'm going to pour this into
With
the baggie.
Food coloring. Okay.
Yeah, with food coloring. Okay, looks like the
Okay.
water from
Okay.
somewhere.
This is good. Now, can we put food coloring in the liquid nitrogen? Will that work?
No, that we can't do.
Oh, it doesn't dissolve in there, huh?
Right. So what I'm going to do here, I need some more liquid nitrogen.
Okay, I'm happy to assist.
Yes, please.
I'm happy to assist. We want to be
Please.
safe with this.
Please give me some liquid nitrogen in that container.
There you are, Dr. Boom.
All right, thank you. So now, when we pour this liquid nitrogen in here, how many say that the liquid nitrogen is going to sink?
I do, I do, I do.
How many say that the liquid nitrogen is going to float?
It's going to float. He does, he does,
Okay.
he does.
How many don't know, don't care? Okay, that's how science is. I mean, either you're right or you're wrong, but you're not bad if you're wrong. You learn something if you're wrong. In fact, you learn more by finding out what doesn't work than what does. And so here we go. Ready? 3, 2, 1.
Okay, go slowly so we can see. Oh. Let's see, if the nitrogen was more dense, it would be at the bottom of that triangular
Well, there
bag.
you have it. So the water looked like it didn't go very far. It just sat on the bottom, and the liquid nitrogen sits on the top. And so the water sinks. So the water is more dense at room temperature than liquid nitrogen is at minus 196 degrees centigrade.
Oh, that's a good little comparison. That's a good little comparison. That's interesting. So if you went to a planet that had liquid nitrogen on top boiling, there may actually be water down beneath it.
That's right.
I mean, maybe.
The water will be frozen, maybe. Oh, now you can't see it so much.
No, not in there. Very cool. That was a good little demo there.
You like that?
Yeah, now this stuff looks pretty cold. This looks like I could damage myself if I'm not careful with it.
Yeah, you know.
I know we've got glasses, we've got gloves when we're using the bigger stuff.
I've spoken to a lot of kids, and they all were like, what would happen if you put your finger in it? You
Oh,
know?
they always ask that, don't they?
And we can't really demonstrate that because we need our fingers. And the kids that want to put their finger in it, they need their fingers too. But I have a friend. I have a workaround. And the workaround is I have a friend at the UCSD Medical Center.
Oh, that's just close by.
Just down the road.
Yep.
His name is George, and he's a good friend of mine.
Uh-huh.
And they get cadavers in for medical science,
Oh,
for
medical,
dissecting and stuff
okay,
like that.
cadavers, yeah.
And they don't use the fingers.
Oh.
Because, there's a lot of fingers, and not many doctors doing the fingers.
So they must have fingers galore.
I borrowed a demo finger,
Ah.
and for the viewers' pleasure, whatever you call it, I put it in here and I froze it.
Oh.
And we thought we would show you what it would look like.
Oh.
So this one is, we know this guy's name. I won't tell you until we bring out his finger. He's been out there for about 22 days. And so, here we go. Aha, here we go. This guy's name is Oscar Mayer. Okay, and so my friend is at Vons. Of course, this is a joke, but it's just like
look at that.
it's a hot dog and it's a chicken dog, and it's frozen. And so this would be just like your finger if it was frozen. And so let's see what would happen here if we just slammed it on
Oh, look at that.
Oh, look at that! Now we have Oscar Mayer chips. We have enough for everybody.
So that broke into probably 50 different little pieces. So it's not like it just broke once or twice. That truly shattered.
It's shattered.
That really shattered. It's not quite as if it was as cold. Oh, I know. So students, I suggest the students then should go ahead and take a frozen hot dog out of the freezer at home, which is nowhere near as cold as this is, and, I don't know, drop it on the floor.
Oh, that would be a good experiment. Put it in a plastic
baggie
bag
first, yeah. And I bet it might break into 2 or 3 pieces, but not shatter like this.
Yeah,
That shows you how cold this is. Now, you know what saves us from getting our fingers in here and having shattered fingers?
What?
Our pain receptors. If we were to put our fingers in there for a certain time, we would go, ow! And that saves us.
Oh.
Nature has given us some safety devices called pain receptors. And those are the things that help us keep ourselves safe.
Good thing.
Yes.
So, what else do we have to show these guys?
Okay, so we've talked about liquid nitrogen, we've talked about density, we've talked about gas to liquid, we've talked about gaining energy from the environment. We talked about
the Leidenfrost effect.
Leidenfrost effect. We showed a little bit of nitrogen in a bucket of water over there, which kind of made that cool looking fog. How about this? How about a cold volcano?
Oh, yeah.
You want to do a cold volcano? We can leave them with the cold volcano.
Cold
So-
volcano would be great.
Volcanoes, we think of on the Earth, volcanoes as being hot. In fact, volcanoes simply are defined as expanding gases that erupt, and they can erupt the gas and the liquid and solids inside of some formation. On the Earth here, it happens to be magma and the like. But on other planets, there may be liquefied ammonia, a liquefied methane, other things that are liquefied. And they have volcanoes on there. So we want to kind of have a mix of that and show you in some warm soapy water. Dr. Boom, I want you to raise the liquid in here just up to this black line. See that black line right there?
So pour a little bit
Yeah,
in.
so you pour a little in, see how it'll bubble up.
Yeah.
So he's just going to show you the concept of bringing this volume up, and this is our mark that we want to go to. Okay?
Yep.
So, and then I think that'll be it. So
Okay.
just up to that line, no more?
Right. Okay. You give me a countdown.
Have a countdown.
Yeah.
Okay. 3, 2, 1, go. Whoa! Dr. Boom!
I did it. I did
You
it. I raised
did
it to the line.
You went over the
I
line.
raised it to the line.
And look, it's a true volcano. We have gases. Down below, we have some liquid. And look, I can reach my hand in here and pull out solids.
Wow.
It's just ice,
Solids,
but it
liquids.
represents a solid.
Yes, indeed.
So we have gases, liquids, solids right here in this simple little demonstration. And we hope that any time now that you're thinking about a volcano, don't always think about only Earth. There's a lot of other planets and moons out there that a lot of good science ready for you to go find out. Isn't that awesome?
That's for sure. That was really cool.
Good.
We'll have to clean up the table saw now. It's all wet. And
That's okay. We'll do that. All right. I think that's it from us, from General Atomics, from our modified workshop here. States of Matter, Part 2 on liquid nitrogen.
Glad to
Thank
be
you
with
very
you.
much.